It's one small step for man, one giant leap for mankind.
Only within the past 100 years has space exploration become possible for mankind. Today, space remains difficult and expensive to discover. Each year, Arizona Near Space Research makes it possible for more than 100 students to explore the edge of space using high-altitude balloons. Arizona Near Space Research is a non-profit organization that promotes science, technology, education, and mathematics through amateur radio and high-altitude balloons.
We've always felt that students should be involved in our projects, because it's a medium that it's got to start, it's got to finish. You can theorize, you can design, you can build, you can test, you can actually fly, and you can analyze the data, all in the matter of a semester.
When did we start building this? Like
ages ago.
a month and a half ago?
About a month.
So it's been like 6 weeks.
And we finished this morning.
To the
Yeah, we wrapped it in duct tape and we put fleece inside.
Okay, a typical balloon flight, one involving students, would probably start very early, where we have breakfast and we commute out to the launch site. Once we're there though, we try to get there an hour before launch. And so it takes about an hour to tie in the payloads, check everything, make sure that they're working, and then about 20 minutes to launch, we'll start the balloon inflation.
Radios must be checked, the communication beacons must be prepared, and the balloon setup assembled for student satellite prototypes. Jack is unwinding the tow line. Student payloads will be attached with metal couplers approximately 10 feet apart on this line.
Put that loop through that top. We're going to put slack, so the weight will be through the package on this rod, and then we'll do another one and do that on the bottom. Okay?
The most important payloads carried by the balloon are recovery beacons. Inside each recovery beacon, a GPS will transmit the coordinates of the balloon's position to the chase team on the ground. Other important payloads include cameras, both still and video. They collect visual data during the flight, which helps students better understand atmospheric conditions and the behavior of payloads in flight.
This box, it carries a standard payload. We got the camera, we got an accelerometer in there, we got a temperature sensor, but the main project with this box is these 4 booms we have attached, which are moment arms, and our goal is to dampen the rotation rate of the balloon sets on the string. So hopefully we'll stabilize the payloads enough that the cameras will get steady shots instead of it just all spinning around.
The inside has a series of insulative layers to hold all the heat in as it gets to higher altitudes. Our probe is equipped with a pressure sensor and 2 thermal probes, one to measure the temperature on the inside, the other to measure the atmospheric temperature on the outside. It also takes still shot images once every minute and a half, so every 90 seconds. It uses these pendulums here to try and stabilize its spin rate, as the system that it's floating on is rather chaotic.
High-altitude balloons are made of latex and filled with helium. It takes about 2 cylinders of helium to fill the balloon to a diameter of 8 feet.
The balloon can be anywhere from 12 to about maybe 16 foot in diameter at launch, and due to the pressure changes as it goes up, that balloon gets larger and larger.
A balloon with a diameter of 8 feet will lift 10 to 15 pounds of payload weight. A parachute is attached directly beneath the balloon to decrease the return velocity.
The parachute opens immediately, and you can see that in the video, but the air is so thin it's not very useful. And but then as the air gets denser, the parachute will be more and more effective, and it will slow it down. And by the time it reaches the ground, maybe 45 minutes later, it's traveling about 12 to 15 miles an hour.
Weights hung below the balloon match the calculated amount of lift so that it is easy to determine when the balloon has been filled with enough helium. When the weights begin rising off the ground, the gas is turned off and the balloon is capped. All the beacons are double-checked for proper function as they are solely responsible for the balloon's recovery. It is standard procedure to fly 2 to 3 beacons for safety. Last-minute instructions are given, and students take their positions on the launch line.
So once we have the balloon inflated and all the payloads are laid out, we'll essentially have the balloon upwind. So if the wind is going, say, that direction, all the payloads would be there so that the balloon will rise up, travel over them, and pick up the payloads.
So what we're trying to do is we're at least trying to line up with the wind. Everyone push a little that way.
We have launch of ANSR, flight 64.
The balloon usually travels anywhere from 800 to about 1,200 foot per minute. We can control that. That's the ascent rate by putting in either more or less helium. If we put in more helium, it goes up faster, but not as high, because once it reaches about 50 foot in diameter, the balloon will burst.
During the ascent, decreasing atmospheric pressure causes the balloon to expand to many times its original size. As the balloon continues its journey upward, temperatures fall below -30 degrees in some regions of the atmosphere. Winds encountered in the jet stream cause the balloon to attain velocities over 100 miles per hour. A high-altitude balloon will rise to the very edge of space, allowing atmospheric sensors to collect data above 90,000 feet. Onboard camera payloads capture the beauty of planet Earth by taking photos and video throughout the flight. Typically, it will take about an hour and a half for the balloon to reach 90,000 feet. Even at this altitude, the balloon remains visible to the naked eye. The chase teams quickly pull over and try to spot the balloon in hopes of observing the burst. Directly after burst, the atmosphere is so thin the parachute will not be very effective. The packages fall, reaching velocities of over 100 miles per hour until 40,000 feet.
Most of our failures occur right there, and so we have to be structurally, sound and electrically, sound as well. And then it takes about 45 minutes for the balloon, for the payloads to parachute down.
Yes, sir, went out to 300.
In each chase vehicle, a special piece of equipment called a ham radio receiver is able to detect when the recovery beacons on board the balloon transmit a GPS coordinate.
But we have tracking beacons, and this is one of the tracking beacons that the students here at Embry-Riddle built, and it's essentially a GPS receiver, this little board here, and it goes over to a modem and then to a transmitter, and that sends down the GPS information. And so we have displays in our vehicles that will then take that GPS information, put it on like a map, including Google, Earth, and we can actually see where the balloon is.
Chase teams try to be within a few miles of the landing point prior to touchdown.
Okay, there's one.
Yeah, trying to find the balloon with some binoculars, over.
Hold on.
After the balloon has burst, the team has only 45 minutes before the payloads will be on the ground. The flight path is examined and drivers use road maps to help figure out the best route to the anticipated landing site.
Now this shows the road going back. You can see here, here's where we're at.
Yep.
Here's 300, here's where our balloon is. This shows a bigger road back here.
When the balloon has descended to an altitude of 1,000 feet, the recovery beacons transmit one last GPS coordinate before dropping out of range.
We've been within probably 50 feet of it landing a couple of times. One of our students, Elijah Brown, and I, we were out and he was driving and I told him, back up, back up, back up. And the balloon missed landing in the back of the pickup truck by about 25 feet. That was fun.
That way?
Just landed.
Out that way.
I copy you. I'm heading up.
Okay, we're 1 mile away from it.
Once the chase team is within a mile of the payloads, they are close enough the recovery beacons can transmit an exact GPS coordinate of the landing site. Students enter this coordinate into a handheld GPS and take off in search of their payloads. Professors aren't far behind. Students conduct a visual inspection of the landing site and their payloads.
I hope our chip's still in there.
Students cut their payloads free of the tow string and collect the data gathered during the flight.
They provided what they were supposed to upon launch.
The morning concludes with pictures, handshakes, and congratulations. The flight is complete when each team has recovered their payload and collected their data. Although the flight is over, for some students, it is just beginning.
For many, flying the balloon is not the end to itself. As I said, the students at the collegiate level are allowed to build the design and build their own payloads. And so they'll spend a full semester doing that, and maybe 2 semesters where they'll add on the second semester more complexity to their experiments that they're flying. Generally, we have pre-flight reviews, we'll have the flight, and then they will digest their information, and then we do the second semester, and at the end of the second semester flight, we will have a symposium. The symposium alternates between ASU and U of A, and there's where the students get up and talk about their results. And so there's some public speaking, and they talk about their design and then what the results were, and sometimes what they would do better next time.
These students are tomorrow's engineers and space scientists. Because of Arizona Near Space Research, these students were able to design a satellite prototype and send it to the edge of space. Anyone can become involved in high-altitude ballooning.
We're not the only group in the country. There's a number of groups now that are almost in every state. So if you'd like to get involved with that, Google Space Grant in your state and contact those people. And they probably have a balloon program within almost every state now.
We hope that you have enjoyed this program on high-altitude balloons. Please visit our website at www.ansr.org for more information.